Oh, you got it? All right. Yeah, transposing maybe.
Hi, everyone. Welcome to Lab 5. This lab is on linear algebra and solving higher order ODEs, and this will be relevant to your current homework 5. This lab will not be on the midterm. The midterm will be on labs 1 to 4. And the type of question I could ask in the midterm will not be asking you to write the code from scratch. That's not reasonable. What I could do is to ask conceptual questions like in or everywhere participation surveys, or I can provide you a code with some bug and maybe provide you the error and let you find where the error is. Okay. And for this lab, I'll briefly introduce the linear algebra that could be helpful for your homework. And then we'll go into solving higher order ODEs. There's some extra steps that we'll need to take to solve second order and third order, etc., higher order ODEs. So to define vectors or matrices in Python, you can use NumPy's array. If you have a 1D array, this automatically becomes a vector. If you have two vectors and you want to find the dot product between them, in Python, it's using the at symbol. So u at v is equal to u dot v, and it returns a number. If you want to find the norm of a vector, there are several types of norms that you can define. Usually we define the 2 norm or the Euclidean norm when you calculate distance. It's the square root of the sum of the squares. It's the 2 norm. And the syntax is from the NumPy linear algebra submodule, you call the function norm. And the default is a 2 norm. But if you want to do 1 norm or infinite or maximum norm, you can supply an extra argument here so that you can take the 1 norm or the infinite norm. To define a matrix, it's basically a 2-dimensional array. So here I have defined matrix A and matrix B. If you want to multiply the matrices, it's still, the syntax is at. So A at B is basically matrix product of A times B. You can also verify their shape should follow that the inner dimensions should match. So 2 times 4 and 4 times 3. So the inner dimension match, so they can perform matrix multiplication. So if you do the converse, that will not be true, because if you do a B at A, because their shape doesn't match, it will give you an error. So the error here says that there's a mismatch in the dimension because it's 2 times 3. If you want to find the determinant of a matrix, here defined as A, you use in the submodule det as determinant. You can find the inverse of the matrix using linear algebra inverse function. And you can use the inverse matrix to find the solution of a linear system. So you have the inverse matrix multiplied by B, you get the X. You can, but this is usually very slow because if you invert a large matrix, it's very computationally heavy. So what we usually do is to solve linear system with linear algebra.solve. So you first input the matrix, then you input the vector, and it will give you the result. So solve matrix A, vector B, you get the vector X. Any question? This should cover your homework's linear algebra portion. Now let's go on to solving higher order ODEs. This is, I think, very important actually, because we will reuse these content in future labs. So be careful, how do we convert higher order ODEs to first order ODEs? So suppose we have a higher order ODE that's here, second order, and you have a general function. And we have some initial conditions, and we have two initial conditions because the order of this ODE is second order. And if we want to solve this in Python, we want to make this second order ODE into a system of first order ODEs. So we take a more complex problem to a simpler problem. But how do we do that? So the algorithm is first rewrite the ODE to standard form. By standard form, I mean on the left-hand side, we only have the highest order derivative, and its coefficient is 1. So here we have already in the standard form. So y double prime is equal to some generic function dependent on the independent variable, the dependent variable, and its first derivative. Okay. Usually, sometimes it does come with a coefficient, or some terms on the left, you need to rewrite into the standard form. The second step is to rewrite or define auxiliary variables. By that, I mean I would define a variable called W0 that will be equal to the original function, so y of x. And I will define W1 as the first derivative. And note that the number of auxiliary variable is equal to the order of the ODE. You'll see why we need to define auxiliary variable, because that makes the presentation of the ODE much simpler. So after you have defined the auxiliary variable, you want to take the derivative of the auxiliary variable, then rewrite fully in terms of auxiliary variable. So we take the derivative of W0. So W0 prime is, if we evaluate this is y prime. And y prime, if we rewrite in terms of auxiliary variable, is W1. And similarly, we take the derivative of W1, which is W1 prime. And W1 is y prime. So y prime, and then taking the derivative. So this is y double prime. But we want to rewrite the y double prime in terms of auxiliary variable W. So here, when we got to the highest order here, we use the original ODE. So we go back to the standard form here. So we see that y double prime is f of x, y, and y prime. And then we also need to rewrite this in terms of auxiliary variable. So f of x is the same, but y of x is defined as W0. And then y prime is defined as W1. And the fourth thing is to rewrite the initial condition in terms of auxiliary variable. So the initial condition for W0 is just y of 0. And y of 0 here we define as C0. And W of 1 of 0 is y prime of 0. And here we define as C1. So after all this work, what have we done? We basically transformed this second order ODE into a system of first order ODE. And this is here. So the system is W0 prime is equal to W1. And W1 prime is equal to a function of x, W0, and W1. Subject to initial condition of W0 of 0 is C0, and W1 of 0 is C1. So here you can see that after the transformation, we don't see y here. We only see w, the auxiliary variable. So we completely rewritten the original dependent variable to auxiliary variable. Okay, any questions? So let's do the first example. The first example is we are given an ODE, some initial conditions, some domain, and they ask you what's the order. So we find the highest derivative, it's 4. So it's a fourth order ODE. Is the ODE linear? So we look at the y's. Y doesn't multiply by each other, but it is an argument of a nonlinear function cosine. So it's not linear. Is it homogeneous? There's a -1 term, so it's not homogeneous. Rewrite the ODE into a system of first order ODEs using auxiliary variables. So we take this and then we apply our algorithm. So the first step is to write in standard form. So the standard form means that we move everything to the right. And then we also divide everything by this coefficient. So we have y to the 4th is equal to -6y to y3 prime minus 9 y double prime. Or if we are moving it to the right, this should be plus. And then this should be -2y prime minus 4 cosine of y minus 8 sine of x plus 1. So I first move this to the right, and then I want to take care of the coefficient. So I divide everything by 3. Okay, and 6 divided by 3 is 2, and 9 divided by 3 is 3. So I have rewritten the ODE into a standard form. Second step is to rewrite in auxiliary variable. And we define that. So we define W0 as the original function, W1 as first derivative, W2 is the second derivative, and W3 is the third derivative. Okay, we have made the definition. Third step is to take derivative, then rewrite in terms of auxiliary variable. So W0 prime is y prime, and y prime is defined as W1. W1 prime is y prime, then prime, and it's defined as W2. W2 prime is y double prime, and then take derivative, which is defined as W3. And then W3 prime is the fourth order derivative y. And how is it defined? It's defined in the standard form. So I just need to copy this copy everything in the standard form, copy, and then I paste it here. Okay. So now we have defined the system of ODEs. And then the fourth thing is to rewrite the initial condition. The initial condition was these. So we rewrite it. So W0 of 0 should be Y of 0, which is 1.2. W1 of 0 is first derivatives at the start, and it's 2.5. And we do similar thing with W2, which is Y double prime at 0. Can't write this. It should be 1.3. And then W3 of 0 is Y to the third derivative starting at 0, and it's 3.2. So what we have done is to rewrite the fourth order ODE into a system of first order ODEs. And the first three are really simple. It's just chained 0, 1, 1, 2, 2, 3. And the last one is derived from the first thing that we found, the standard form. And then the initial condition we also rewritten. So after rewriting these, we don't look at the Y's, we only look at the W's. Okay, any questions? Okay. And you can practice rewriting higher order ODEs on yourself on papers. So here we present some higher order ODEs, and I'll give 10 minutes. Oh,
Oh, okay. Yeah, thank God. Yeah, that we had to type it out. No, yes. Thank you. We have commencement term on Monday, and then transport the lowers like end of the month. Yeah, but transport isn't pursuing that because he's afraid of ChatGPT now. Even though it's not good, bro, it cannot help. It's not good. Like we try to use it and it just doesn't. Like unless you get the paid version and you really like massage it. Yeah. That means we have to learn it all. Huh? Yeah, right. You might give us an equation sheet, maybe. But yeah. Everything in additional notation is weird too. Yeah. Very like, but besides that, sounds great.
So. Is to take a screenshot. So for example, if you have a people over attention, take a screenshot and then you just do so, the good way is that you have attention. But the picture is.
Okay, because I tried to do that, like for a different method.
So inside a post, inside a context.
I'm better.
This is transformation. This is for accessibility. So, accessibility is the which explains it.
Oh, wow.
So that's not the point.
Not very good design.
This guy.
Wait, but when you just, when you just, like.
The one, the natural one. No, I didn't see the natural one.
I think it doesn't like,
Oh, and then you got it because you did FN two, right? Like,
so yeah, F2 in Windows is really
oh, right.
because currently you have to is
Yeah.
your function. So because we have here is a function.
Mhm. And this is like
Okay. Are we good at writing? Rewriting all these? Okay. 5 more minutes. Okay, let's look at the practice problem. So the practice problem we have here. So the highest order of this ODE is to the 6th. So this is a 6th order ODE. Is it linear? It has a natural log of y, so it's nonlinear. Is it homogeneous? There's a K9 constant, so it's non-homogeneous. So if we want to rewrite this in terms of a system of first order ODE, the first thing to do is to rewrite in terms of y of 6. So y of 6 is equal to everything we bring to the right. So this whole thing we move to the right. So we have plus k2 y to the 5th derivative minus k3 y 4th derivative plus k4 y 3rd derivative plus k5 y 2nd derivative minus k6 y derivative minus k7 natural log of y plus k8. Now I'm just copying the right side, e to the x plus k9. And because there's a k1 coefficient, we want to divide everything on the right by k1. So I have divided by k1 for all the coefficients. What the heck? Can't write. Okay, that's the first step. The second step is to define auxiliary variables. So we have W0 is y, W1 is y prime, W2 should be W is y double prime, W3 is y triple prime, W4 is y to the 4th order derivative, and W5 is y to the 5th order derivative. Again, the number of auxiliary variable is equal to the order of the ODE. So you have 6 auxiliary variable. And then you take the derivative of each of them. So if you take the derivative, this is y1, y prime, and y prime is W1. And then W1 prime is W2. W2 prime is W3. W3 prime is W4. And W4 prime is W5. And W5 prime, you don't have a W6. So here, you're taking the derivative of the 5th order derivative. So this is y to the 6th order derivative. And you already calculated in step 1, this is this whole thing. So now you have a system of first order ODEs. And now you can rewrite your initial conditions. So your initial condition is W0 at x0 is C0. W1 at x0 is C1, and etc. So we have till W5 of x0 is C5. Any questions? Okay, nice. This is very important because we will be using this multiple times in the future and highly possible on midterm 2. So I'm emphasizing this so that you know.
Is that it?
What?
That was it for that. Okay, well, up until the rewrite the initial condition.
What's that? Midterm? Or
No, for this practice problem 1, part B.
yes,
All we
that's it.
have to write is up to like the initial condition, rewrite the initial condition.
Yes. Yeah, we're not solving it yet because we'll need some more tools to solve it. Yeah. Yeah, this problem is made very complex, so you understand the steps. But the most complex step is actually rewrite it. That's it. Because here you're just pairing 0, 1, 1, 2, 2, 3. And then you have to realize the highest order one you get from the standard form. Okay. Any other questions? Okay, now we have transformed higher order ODEs to a system of first order ODEs, and we are equipped to solve first order ODEs. So we can use the SciPy integrate solve IVP, but the syntax will be a little different than before. So watch the syntax closely. So for this example, we have a second order ODE that is linear because it doesn't have y as a nonlinear argument or multiplied by each other. But we do have a -3, so this is a non-homogeneous ODE. We have two initial conditions, which matches our second order. So we want to find the exact particular solution with Wolfram alpha. I think by now you have already know how to use it. You just type this in with the initial condition, and then you'll get this particular solution. And you can also take the derivative of this pretty easily without retyping anything. So let me show you. So if you got the particular solution here, which is this, you click on it, then the prompt will become the analytical form of the solution. If you want to take the derivative, bracket the solution, and you type d dx, and now you get the first derivative. Okay, and then, yeah, so this is the first derivative, so I have copied that down here. Then again, we want to rewrite this in terms of auxiliary variable. So rewrite this. This should be much easier because we have done the harder example. Okay, let's do that again. So first, standard form. So y double prime is equal to minus y prime minus y minus sine of x plus 3. Then we define auxiliary variable. W0 is y, and then W1 is y prime. And then we take the derivative of each of those. So W0 should be y prime, and y prime is W1. And then W1 prime is y double prime, which we get from step 1. So this is minus y prime minus y minus sine of x plus 3. And then we rewrite this in terms of w. So y prime is defined as W1, and y is defined as W0, and then sine of x plus 3. So here is our system of first order ODEs. And then the initial condition is W0 of 0 is 1 here. And then W1, which is the first derivative at initial point, is 2. So we have rewritten this as a system of first order ODEs. Any questions? Okay. And the question asks you to solve the ODE using solve IVP. So to do that, we first get the original ODE standard form. So we input the y prime, y double prime into there. So it's dependent on x, y, and y prime. So actually, let's code this up. So if you have this ODE, then y double prime is equal to the lambda function. It's dependent on the independent variable x, the dependent variable y, but also it depends on y prime. And then you move everything here to the right. So it's minus y prime minus y, and then minus sine of x, and then plus 3. And I won't type in the exact analytic solution again because that's pretty easy. You have plenty of practice. You just need to remember you have to np.exp, np.sine, np.square root. If you don't use np, it will raise an error. So here are the exact solution for the original function and the first derivative. And also take care of the order of operations. So if you've got parentheses, take care of those. And the important part is to solve this with solve IVP. So we have an x here, so x minimum is 0, and x maximum is 20, with a dx of 0.1. So we can define the x numerical x as NP range from the minimum to the maximum, but we do want to include the endpoint, so we plus the dx at the step of dx. So these are our numerical, oh, this is x. So this is our numerical points in x. Okay, after having the points, we want to define the ODE system. So remember in last time, we have in the SciPy integrate solve IVP, the first thing is the functions. So in this case, instead of a first order ODE, we have a system of ODEs. So the method that we define the system of ODE is that it's equal to, again, a lambda function that takes in the independent variable, which is x, and a vector of dependent variable, z. So here, x is independent variable. Z is a list of dependent variables. So for a second order ODE, it's y, and y prime. Okay. So within this function, we'll have a list. And in this list, we'll have the first equation. So W0 prime equals to W1. So this will be, let's call this dw dx. So dw0 dx, evaluated at x, and then z, and all the argument of z. So this star in front of a list, meaning that we are unpacking all the elements of this list. So this is the same as saying x of z0 and z1, but I'm writing it compactly as star of z. So this is the first line. The second line is the second line of our ODE, which is W1 prime. So we call that dw1 dx evaluated at the independent variable and all the dependent variable. Okay, if you run this now, it won't return you anything good. The reason is because we have not defined W0 of x and W1, dw1 dx. So we need to define those. And these are also lambda functions. And it should take the same arguments. So it takes the independent variable, the dependent variable, and the first derivative. But in our case, we have already rewritten them into W0 and W1. So let's rewrite in terms of, so it's x, W0, and W1. And then the first derivative of W0 is W1. So just put a W1 here. And again, the W1 dx should be dependent on independent variable, W0 and W1. And the equation is here. You have two options. You can rewrite this, or you can use the double prime function you have defined before. So to illustrate this, you can use y prime 2 evaluated at x, and then W0 is y, so you evaluate W0 here, and then W1 is y prime, so you evaluate W1 here. Or alternatively, you can also rewrite everything. So if you rewrite it, it's minus W1, minus W0, minus NP son of x plus 3. It's the same thing. So now you evaluate this function, you will get some number. So that's meaning that your function is good. If you doesn't get anything after evaluating it, in some sort of trouble. And within the solve IVP, the second argument is so this is the function, the system of ODEs. And the second thing we want is the list of left and right boundaries. So first I define a list, and the left bound is x minimum, and the right bound is x maximum. So x min to x max. And the third thing is the initial conditions. So a list of initial conditions. So because we have a second order ODE, we have two initial conditions. And the initial conditions are in order. So the order is the original functions at initial point, and then the first derivative at initial point. So y of 0 in the problem is 1, and y prime of 0 is 2. So we type in 1, 2. And then the fourth argument is optional. It's these t, or the time steps that we want to evaluate at. And in this case, it's x numerical. If we run this, we get an error, and the error says type error. It says unhashable NumPy array. So let's see what's going on. So I think it is because we haven't inputted the keyword argument. This should be t span, t eval. Okay, that should be good. So remember to put this key argument. So the result of this evaluation is the solution. But these are all dictionaries. The main thing that we want is actually y. So here. So this is the result. So if you want to index a dictionary, you do dot y. And now you selected the array. And you note that this array has two elements. So this is the first element. And we also have a second element. So the first element is the original function. The second element is the first derivative. And you can unpack this very easily by assigning them to variables. So for example, because the first element is the result, I can say y of psi pi. And then you do a comma. And the second argument can be y of psi pi. So y prime of psi pi. And this will unpack the list. So now if you look at y psi pi, this is a list. And y prime of psi pi is also a list. And if you want to plot this, you can do plot x numerical, comma, the original function. So this is the solution of the original function. You can verify the initial condition is indeed at 1, and then the slope is approximately 2. You can also plot the first derivative. So x numerical, y prime from psi pi. And this is the first derivative. And you can verify the first derivative initial condition is indeed 2. And then you can do the plotting as instructed, but I think at this point, everyone should know how to plot things with subplots, so I won't show that. So basically, what we got from the plot is that if we plot the exact solution with the SciPy solution, they coincide very well because the error is small. Any questions? Let's try this out with the practice problem.
Yes.
Okay, let's briefly go over the practice problem. So we have a real system here, and this is second order because the highest derivative is second. This is linear, and this is homogeneous. To rewrite it into a system, first write it into standard form. So y double prime is equal to negative c divided by m, y prime minus k divided by m. So I'm moving the m constant to the right times y. Second step, define auxiliary variable. W0 is y, and then W1 is y prime. We have two auxiliary variable because we have a second order ODE. We then take the derivative of each of the variables. So W0 prime is y prime, which is defined as W1. And then W1 prime is y double prime. And we already rewritten y double prime. So we have everything copied down, but we do want to rewrite it in terms of W. So we have minus c divided by m, y prime, which is defined as W1, minus k divided by m of y, and y is defined as W0. And then we want to find the initial conditions, which is W0 of 0 is 0 meters. And then W1 of 0 is 0.1 meters per second. So this is our ODE system with the initial conditions. Any questions? Okay, and then we want to code this up in solve IVP. The most important part is to get the system of ODEs correct. So the first argument is ODE system. And the system should be defined as lambda, the independent variable t, and then dependent variable list, which is z. Define as a list. And the first element of the list is our first ODE. So W0, dW0 dt. dW0 dt. Evaluated at t and all the elements of z. Then the second thing is W1 prime. So dW1 dt evaluated at the independent variable and all elements of dependent variable. And we want to define dW0 dt and dW1 dt. And they should also take in t, W0 and W1, all in terms of auxiliary variables. And then W0 prime is W1. So we write W1 here. And then W1 prime is the y double prime. So let's define y prime 2 is equal to minus c divided by m. So it should be a function. So lambda of t, y, y prime is minus c divided by m times y prime minus k divided by m times y. So you can evaluate dW1 dt with y double prime. So that should be t W0 W1. And then to test if this actually works, give it a number. So let's say initial value, then gives some random points. Okay, it doesn't work. And it says c is not defined. So we haven't defined the constant c, m, and then k. So let's see, how do we define those? C, m, k. So we have the mass, which is 1,000 kilograms. Oh, it's the mass. And then the K is spring constant, 2,000 Newton per meter. And then the damping constant, 500. And then it also asks us to do without damper and with damper. So if it's with damper, it's 500. If it's without, it's 0, because there is no damping. Okay, so we'll keep that in mind. So let's first do without damper. And now it works. Nice. So the second argument is the left and right boundaries. The boundaries are defined here. So let's define t. So t minimum is 0, t maximum is 10, and dt is 0.1. So t numeric should be NP range from t minimum to t maximum, but including the maximum, so plus dt, comma, the step size dt. And we can see we do have a list of points. So the left bound should be t numerical of 0, and the right bound should be t numerical of -1, the last element. And then we input the initial conditions. The initial conditions were 0 meters and then 0.1 meters per second. So 0, 0.1. And then finally, we input t eval, which is the t points we want evaluation. So that's t numerical. I missed a comma. Okay. And the solver successfully reached the end. So we want the result y. So access it dot y. And this array has 2 elements. So the first one corresponds to original function. Second one is first derivative. So we can assign y of scipy and y prime of scipy to this. And then we can plot it. So t numerical and then y scipy. So this is the position. As expected, it's oscillating because it's vibration. And then we can also plot the derivative. So the derivative of a sinusoidal wave is also a cosine wave. So this is also expected. So it also lets you to plot. So this is without damper. What if it's with damper? So if it's with damper, it's 500. We rerun this. We see that if we do have a damper, the oscillation dies down over time. And you can do this by copy and pasting the code, but that's not so efficient. So for example, in part E, you want to test dampers with different damping constants. How do you do that? So I'm gonna copy and paste everything here to one single cell so I can transfer it over. Okay, I got everything. So if we want to do multiple constants, do not input it using hard coding. It's very tedious. If I give it 100 lists, you can't do it 100 times. So what you should do is, first the t is the same. And then the constants is, these 2 constants are the same, but c is different. C, we have a list. So we want all these damping constant, but also solving for no damper control, which is 0. So we have a list of c. So we do c list is equal to these stuff. And then plus a 0, which is the no damping control. Okay. And then always put the unit here. So newtons second per meter. We define our second order ODE and our system of first order ODEs. And we want to solve for the solve IVP with different C's. So for C in C list, we want to solve for this. And after solving this, we immediately plot this. So we first establish a figure. So we want a 1/2 figure. On the left, we have the original function. On the right, we have the derivative. So it's 1, 2. I'll set a reasonable figure size. So 12 inches by 5. Okay, so this is our figure. So within each of these for loop, we have different C's. And we have the original function and the derivative. So that for the first of the axes, let's plot the original function. So plot t numerical, comma, the original function by scipy. Then let's also label that with the C. So we can do an F string standing for formatting. So C equals to the variable C. And outside the variable, you put a curly bracket. Okay. And then because we haven't do the legend, so we should put a legend. And because the legend covers up the image, we can actually put the legend outside here. So we'll do that later. But we have seen that for different damping constant, we have different behavior. So the blue one is the original without damping. And the other ones are with more damping. And we'll see that the damping actually helps to mitigate vibration if the damping constant is large. But of course, larger the damping constant, the more expensive the equipment is. Now we can also plot the first derivative, which is the velocity. So y of y prime psi pi. Okay. Because it covers up, and these two use one single legend, so we can just do one legend. But with that one legend, we need to use a special command called bbox to anchor. I usually set it to 1.02 so that it becomes at outside. So this helps you if you have a legend that's really large. And also do a PLT tight layout so that it's not too crowded. Okay, any question? Cool. What did I want to say? Okay, yeah, this is it for the SciPy part. Last time we also learned our own numerical method of forward Euler's method. And that's basically for first order ODEs. But now we have a system of first order ODEs, so we can use this for the system and solve it step by step. And to illustrate this, let's consider the ODE that we have encountered before, but this time calculate by hand the value of the first and the second step. Okay, let's do that. Okay. Okay, so we have this ODE and we have the forward Euler method. So if we want to calculate by hand the first step, then we start by the lowest order. So this is zero order and the first order derivative. So we have y of 0.1, which is the I plus 1. So we have already know that delta x here should be equal to 0.1. Is equal to y of 0, the initial value, plus y prime of 0 times delta x. And this is y0 is 1. And then y prime of 0 is 2. Delta x is 0.1. So this should be what, 1.2. Okay, so we have solved this. And then y prime of 0.1. Again, we use our forward Euler. So the original function, which is here y prime, starting at 0, plus its derivative. So this should be double prime of 0 times delta x. Okay, but what is this thing? Y double prime of 0? We don't have that initial condition, do we? What we can do is to evaluate this. So if we put everything here on the right-hand side, we will have the standard form for y double prime. So minus y prime minus y minus sine of x plus 3. So this we know, so we can evaluate this at 0. So basically this is y prime of 0 plus the derivative, which is minus y prime of 0. So evaluate everything at 0, minus y of 0 minus sine x is 0 plus 3 times delta x. And since we already know the derivative's initial condition is 2, plus minus 2 minus 1 minus 0 plus 3 times delta x, 0.1. And this is minus 3 plus 3, so this is 0. So the first derivative at the first time step is still 2. Any question? So we just do this step by step, but starting from the lowest order. And then for the second step, so y of 0.2, then it should be y of 0.1 times y prime at 0.1 times delta x. Y of 0.1, we calculated 1.2. And then y prime of 0.1, we calculated is 2 times dx 0.1. So this is 1.4. Okay. So we have solved this. And then y prime of 0.2, again, should be y prime of 0.1 plus y double prime of 0.1 times delta x. And for the y double prime, we again use the original ODE. So we have minus y prime of 0.1 minus y of 0.1 minus sine of 0.1 plus 3 times delta x. Can't write. Okay. Y prime of 0.1 we calculated is 2. 2 plus minus 2 minus y of 0.1 is 1.2. Minus sine of 0.1 is already the simplest, so we'll just leave it there. Plus 3 times 0.1. Okay, so if we want to simplify this, this is 2 plus, this is minus 3.2 plus 3 is 0.2. So 0.02 minus 0.1 sine of 0.1. And we can simplify this further. Question? So it's highly possible in midterm 2, this could be on the exam because this demonstrates how you could use numerical algorithm. And you want to solve this numerically using forward Euler's method. We have demonstrated the first 2 steps, but how do we do it in Python code? So here is all the same, define the original ODE and the exact solution, and the exact solution of first derivative. So the different thing will lie on the algorithm for forward Euler. So again, we initialize the forward Euler, but this time we need to initialize 2 lists. Instead of just the original function, we also need the first derivative. So y prime forward. And the length should be the length of the independent variable. And the independent variable in this case is x. So this is x numeric length. So x length. So initialize list to store value. Then we define initial conditions. So what's the first element of y forward and y prime forward? The initial condition was 1 and 2. So let's input that 1 and 2. Then we do forward Euler. But this time we do it twice because we have the original function and the derivative. So for I in range, the length of x minus 1 because we don't want to overflow. We first process the original function. So the original function is y of I plus 1 is equal to y of I plus y prime of I times dx. But we have to be consistent in our wording. So we use the y as y forward. So we'll replace every y as y forward. And then y prime is y prime forward. This is one common pitfall that we are not using the consistent variable. So this is for the forward Euler of original function. Then we'll also do forward Euler of first derivative. So y prime of forward of I plus 1 is equal to it evaluated at I plus its derivative. But that derivative is y double prime. And y double prime we evaluate at the standard form of the original ODE. So what we plus here is we defined the original ODE y prime of 2, evaluated at the current x and the current, so x of I is the current x, and then the current y, which is y forward of I, and the current y prime forward multiplied by dx. Okay, then this. So it says x is not defined. So I defined here is an x numeric. So common pitfall, not using the variables consistently. Where is x? Line 13. So it's here. So I'll replace that x as x numeric. So now it's run through. So let's check. It has some value starting at 1, which is promising. And then the y prime also starting at our initial condition, which is also promising. So let's plot it. So plt.plot for x numeric, the solution y forward. So this is the same as before, so that's good. And then let's also look at the derivative y prime. Also same as before. So you can solve this and plot this using a better method. And you'll see that the forward Euler solution has some deviation from the exact solution because it's not as accurate as the fourth order RK method in SciPy. You can practice this with the damper system. And that's the content for this lab. So I'll be here until 6. So you can keep working or work at your place.